Let us now see the moment of inertia and section modulus for different sections of, for different types of beams. Here, before going to write this different types of beams, let me actually make you understand that we are familiar with this formula. M by I is equal to sigma B by Y. Okay. So this formula could be rewritten in this way: M is equal to sigma B into I by Y. Is it not? Okay. So here, if you actually look at this equation, you say that this refers to suppose if there is any beam, with an applied load, applied momentum, and the sigma B will be the stress in the extreme fibers, either this or this, and I refers to the type of beam, whether it is rectangular or something like this, looking from the end. Okay, and Y refers to what? Distance between the neutral fiber to the extreme fiber to the neutral fiber. So here, now for a fixed value of bending stress, so you know that wood has some bending stress like 20 MPa, steel has some bending stress or any maximum stress like 300 or 400. For this amount of, now for this material, and if you want to keep increasing the value of M, so that means if you want to keep increasing the maximum moment a beam can take, then you have to increase this value, which is actually here. So what is this I? I refers to BDQ by 12 in the case of rectangular beams, Y refers to D by 2. Now this ratio is called as Z. Which is called as a section modulus. So if you are actually choosing between two beams, maybe for your house or maybe for a bridge, something like that, and basically all this, you can say beams are supposed to take bending moment without failure. So that means for the same material, fixed, they have to have maximum value of I by value, that is I divided by Y value, which is called the section modulus, if they have to take more bending moment. So whether you have to go for a circular section, whether you have to go for a square section, whether you have to go for a rectangular section, whether you need to go for a I section or maybe U section is left to you. Okay. So the value of I and Y, the value of I can be found out for all the sections. So you're already familiar about rectangle sections, that is BDQ by 12. So we will try to see what are the values of I and Z for different types of sections now. Okay. Here, let me write this. Then hope so it is clear now. So let us now take the first one, which is a rectangle, because square is a rectangle of both sides equal. Okay. So let us take a rectangle, square or rectangle, BND, a rectangle. For this, so here you have got I. So what is the formula for I, man? Rectangle. I is equal to BDQ by 12. What is the formula for Z? Z is what? I by Y. That is BDQ by 12 divided by D by 2, which becomes how much? BD square by 6. So you need to be familiar. Otherwise, if you substitute to get the answer, people need not have to remember this. Okay. And now, if it is a circular section, guys, if it is a circular section of diameter D, the formula for I is given by pi d to the power of 4 divided by 64. And here, it will be the neutral axis, and the distance to the extreme fiber will be how much? D by 2. d by 2. So in that way z is equal to I by y. So that is pi d to the power of 4 divided by 64 divided by d by 2. So now what will be the answer? Pi d cube by divided by 32. Okay. And now for this I section. Now for this I section I need to explain you before I actually go ahead. Basically, I need to explain you how this I section is same as a rectangular section. Guys, you know it? This is a beam. This is a beam. This is a beam of rectangular section. It's a beam. It's a beam of rectangular section. Now, why is this I section different from rectangular section? So, if you remove material here, if you remove this material here, then it becomes I section. So I section is basically like is equal to the whole rectangle minus these two areas, these two small areas. Understood? Okay. So if you know the moment of inertia of this whole rectangle minus these two rectangles, so moment of inertia, or you can call it as, that is the maximum, I mean, that is a resistive moment that these beams can build up. Okay, so you can find out. So if you suppose if you call this as capital B, if you call this as capital D, if you call this as capital D, and if you call this as capital B, then the moment of inertia of this I sections is actually equal to bigger rectangle moment of inertia minus, see here why I am actually adding and directing is that the centroid of all this comes the same. Now the centroid of a bigger rectangle is along the neutral axis, and the centroid of this smaller rectangles is also along the neutral axis. So I can add and direct. Suppose if it was slightly shifted above or below, I couldn't have done this. Then you need to use what is called as parallel axis theorem. Okay, so now the moment of inertia BD cube by 12 of bigger rectangle minus the moment of inertia of smaller rectangle. So let me call this as small b and small d. This is b, this is b. So in that case it is minus BD cube by 12 for this. Again one more, this one also. It is minus BD cube by 12. Instead of writing like this, I can write this as 2 into, understood no? So you can write this as 2 into small BD cube by 12. So this is how you write this for moment of inertia. So now for this it is easy. So for this you understand what is this moment of inertia, which is this, and then z is, you can directly divide, you can substitute the value of y, then you can divide by y. So how much is y here? Y is actually capital D by 2. Then you get this moment of inertia. You don't have to remember this, you just have to use it in the problem if it is required. Okay, so like this you actually try to remember and try to use the value of y for different type of sections, and also use this value of z. So z refers to section modulus. So this will be useful when you are trying to have different types of sections. Which section is better? If you want to say, then just look for z. If the value of z is good, then the beam can take more load. Okay.